Hello and welcome to lecture 36 of Math 1B03. This actually will be the last of our lectures for this course. I hope you've enjoyed them. Kind of as an interesting tidbit, I actually filmed this lecture the same day as I did lecture 1. So I filmed all the other lectures and I saved the last two for today. So hopefully you've enjoyed them and you got something out of them and combined with the in-class discussion and the quizzes and the assignments, and I hope you're enjoying the course. So today what we're doing is we're looking at section 5.9 on Markov chains. So we're going to kind of still look at some applications of eigenvalues and eigenvectors. And if you're using the 5th edition, you really need to look at section 4.9. They changed the order depending upon your textbook, the edition of your textbook. So today's goal is to look at a special type of discrete dynamical system. Discrete dynamical systems were introduced in lecture 35, and this special type is called a Markov chain. Okay, so I'll make myself disappear, and let's start with our setup here. So our setup is we're looking at what's different from today compared to last time was we're looking at a vector with non-negative entries that add to 1. And we want to give a name to that, and that is called a probability vector. So probability vector. So that's the first thing that we're defining. A stochastic matrix is a square matrix whose columns are all probability vectors. Whose columns are probability vectors. So that's a stochastic matrix. And what a Markov chain is, it's a sequence of probability vectors. So it's a sequence of probability vectors, x0, x1, x2, and so on, and a stochastic matrix, and I should learn how to spell stochastic. There we go, stochastic matrix P, such that really what you have is a dynamical system. So x1 times the first vector gives you, x1 is p times the first vector, x2 is p times x1, x3 is p times x2, and so on. Okay, so really what we're looking at is a special case of a dynamical system. The new condition is on the x0. So the x0 has to be a probability vector, and the other new condition is the matrix A in our dynamical system is a stochastic matrix, which means that all of the columns are probability vectors themselves. Now it turns out that the example that we were looking at last time, where we were looking at migration between Earth and Mars, is actually an example of a Markov chain. Okay, so remember the setup here. We have Earth on the left-hand side, Mars on the right-hand side. 5% of the population of Earth moves to Mars in a given year, and 3% of the population of Mars moves back to Earth. And then the rest of the 95%, if they move on Earth, and the rest of the 97% on Mars move back to Mars. And we had this transition matrix, which kind of captured how people moved between the two planets. So the number of people going from Earth to Earth in terms of percentages is 95%. And the number of people that went from Earth to Mars was 5%. Okay, and then the number of people that went from Mars to Earth was 3%, and the number of people that went from Mars to Mars was 97%. But now if you stare at this matrix right here and you look at the columns, okay, each of the columns sum up to 1, right? So the columns of P are probability vectors. And that implies that the matrix P that we looked at last time was actually a stochastic matrix. So this was a stochastic matrix. So if we look at now the question here that say that this is the distribution of the population between Earth and Mars, so 60% is on Earth and 40% is on Mars, we notice that this is something we looked at again last class, but the x0 here is actually an example of a probability vector, because again, the entries are both positive and they sum to 1. And when last time we were looking at this dynamical system, so x1 was how the population was distributed between the two planets after year 1. x2 was the way the population was distributed between the two planets in year 2, and so on. That dynamical system is actually a Markov chain, because we start with a probability vector, and our matrix that transformed from one year to the next was a stochastic matrix. And last time we looked at this question is if we're given the initial probability vector and we're given a Markov chain, can we say anything about k as k goes to infinity? Now we answered that question in our last lecture, which was you can use diagonalization to get this value. Okay, so in particular, just before we take a break here, we actually showed using diagonalization that over the long term, the vector x will approach the vector 0.375 and 0.625 as k goes to infinity. So we use diagonalization to get at this part information. But what we're going to see in the next part and work towards is you can actually get this answer via a different approach, since we can now use the extra condition that P is a stochastic matrix. So we'll pause here while I get set up for part 2, and I'll see you in the second part.